Hello, everybody. I will be doing a very, very, very beginner introduction to Femap. We'll be looking at possibly the most simple example possible, a cantilevered beam, and we will also be looking at it analytically with regular Eulerian beam theory to check the answer using like equations and stuff, because that's pretty neat. Anyways, let's get into it. I am now sharing my screen, I think. So here's my presentation I made. It's called the Femap Quick Example. And here's our problem statement. Here's what we will be working on. We have a 1" by a 1" by 12" cantilever beam. So the 1" by 1" is like the cross section and it's 12 inches long. We have a 1 pound point load applied at the very tip of the beam, and on the other end is completely fixed. We will be looking at the deflection today. And then on the right here are our material constants. So like I said earlier, we're going to use Femap, and then we're going to look at Matlab to calculate the exact same problem in two completely different ways to show that, this stuff does work. It's pretty cool. Oh, sorry, I wasn't supposed to show that yet. All right, now let's share my other screen. I recorded this earlier and it only showed the PowerPoint, which is really annoying. My goal is to get this done in less than 15 minutes, so let's get right into it. So we're going to open our geometry. I saved my geometry. I made it in SolidWorks, and then after SolidWorks, I saved it as a step file. The first important thing to notice is that it's asking you for a geometry scale factor. That is because it does not actually, Femap and Nastran do not take into account units. So you have to keep track of your units. If you're using inches, stay using inches. If you're using meters, use meters. If you're using pounds, use pounds, and don't mix them up. And if your answers are ever off by like 5 orders of magnitude, I bet it's probably because of units. All right. Now we have our thingy, our cantilevered beam. So what are we going to do? Well, what material is it? Let's define a material. You can't see it, but there's a big block in the way because of zoom. So our material, let's load it. It's like we said before, this specific kind of steel. And now you may notice that our material is populated here. Now we need to make a property. A property is very similar to a material, except it is embedded with a little more information. I'm sure there's other distinctions, but that was my take on it. We will be meshing a block. A block is good to mesh with a volume. So let's use solid volumetric elements. And let's call our property metal. And our material is the steel we made before. And it always pops up. It's asking you for another one. Its ID here is 2. So don't worry about it. We already made it. That's one thing that confused me in the beginning. All right. So now we have our material. We have our property. Let's start meshing. Meshing would be pretty cool. One really easy way to do it would just be to mesh geometry and just mesh a solid. I'm going to put a little extra finesse into it because you guys are worth it. Let's start off by messing with the sizing. So this is an inch, this is an inch, this is 12 inches. Let's try to get perfect cubes everywhere. Let's do 4 cubes per inch. So 4 elements. Number of elements, set number. 4 elements on this line here. 4 elements on this line, 4 elements on this line, 4 elements on this line. And on the other side, when 2 different opposing sides have the same number of elements, that's called a mapped mesh quite often. Now for 48 elements, because this is 12 inches long, 12 times 4 should be 48, I really hope. And if this is done right, we should get really, really nice cubic elements. So I've put essentially little markers where I want the elements to be. So now when we mesh it, it'll see that and just populate the mesh exactly how we want it, hopefully. So let's mesh our geometry. Let's hex mesh solids. What a hex mesh is a hex is what they call the very square element. And the square is very special because it lets you do your simulations quicker. It has less degrees of freedom than a tetrahedron. Okay, a tetrahedron has fewer degrees of freedom, but it's very stiff artificially. So you have to use a second order tetrahedron, and then that gives you more degrees of freedom. Not that it really matters. This is very introductory, but I truthfully just very much enjoy how this looks. It just looks way nicer to me. So we meshed it. Great job. Now let's apply our boundary conditions. So that's going to be under model. And then let's apply our load first. Our load is 1 pound. Right click on load definitions. Let's put it on a surface. And I feel like it should be on this surface. And we could look at this thing here. I want it to point downwards as per the problem statement. It's symmetrical, it doesn't matter, but I don't know. I'm putting 1 as my value. There is no unit attached because, like I said earlier, it doesn't, Femap and Nastran don't take into account units, so you have to be very specific and keep good track of them. So that's 1 pound. I'm working in pounds. I accidentally put it in the opposite direction. I could have done -1 pounds and it would go in the other direction, but it doesn't matter, so I'm not going to fix it. Let's add a constraint. I'm going to call it fixed, since that's the type of constraint it is, and then apply it on a surface. You can click this highlighter to see what you've actually selected in case you're ever confused. It's really convenient. And I'm going to call it fixed again. And ta-da, we now have a load. We have a fixed boundary constraint. To my knowledge, the whole problem set up exactly how I said earlier. And so all that leaves for us to do is to actually analyze it, which is the fun part. And we get to post-process it. So under analysis, right click on it, click manage. Let's create a new one. Let's call this Max's tutorial. And then here is where you could choose your analysis type. So I'm going to choose static. And then let's analyze it. Hopefully everything goes right. If you get any error messages, they'll show up in this bottom part here or in your FO6 file. This is, if things fail, you can check, you can read like what actually caused it to fail here. So it's very useful. For our purposes, not very important though, since that's, I don't know, I would say that's pretty advanced reading the FO6 and like troubleshooting and stuff. So anyways, our set is complete. A set is kind of like a name for your results in a way. So here they are. Let's post-process them. Let's contour them and then select our set that we're contouring. So that's essentially what we just ran. And then let's look at the total translation. How far has everything moved? And nothing's shown up, but that's just because we haven't put on the contours yet. So look in the top right here, we have 0.00002379. Remember that number, that's a very important number because I also calculated something like that in Matlab. Here we go. If you want to post-process it, make it look pretty, you can take away all this gunk you don't need. You can make it wiggle if you want. This is good to see if it's behaving as you expect. It looks like it's wiggling quite a bit, but that's not a problem because it is being scaled. So if you want to look at the actual deformations, they're super, super small. Keep in mind we got a giant block and it's 1 pound applied to it, so it shouldn't be hardly any deformation. So this is the real one, and this is the scaled one. Hopefully that's clear. That confused me when I started personally. So, okay. So here's our number, 0.0002379. Now let's look at MATLAB at our analytical number. And that's right here. All right. So actually, before I do that, I'm going to show you like the equations I used. So this is my analytical solution. Shoot, am I sharing my screen? There we go. Okay, here's my analytical solution. My area moment of inertia, which is this I thing here. This represents the geometric stiffness. So the stiffness of a beam because of the geometry of the beam. That is this for our specific cross section. Our base and our height is 1 inch, like we said before, and that makes our I value this number, 1/12. And then plug it into this equation, which I so conveniently pulled from the internet. And that gives me this equation. I plug in my values, my 1 pound force, my 12-inch length, my modulus of elasticity of this big number here, my area moment of inertia, and I get a deflection of 0. So this, you got this thing on the end here. So it's 0.0002383. And just to prove that to you guys, here's my MATLAB script. Okay, here we go. Yep, right here. So all my constants are up here. I calculated my area moment of inertia, and then my deflection is this number. Pretty neat. Now, how cool is that? That number is super, super, super close to what Femap says. And these are two completely different approach converging on the same answer. So that makes me feel like it's probably done correctly. Anyways, I hope you liked it. I'm planning on maybe doing some more videos. For my club, I was thinking I would do some composites and I would talk about strength ratios, maybe bolt calculations, and stuff that might seem pretty helpful for my club. If you have any questions, I know I went through this pretty quickly. Please DM me or, ask in the comments or something. Yeah, whatever. But thank you for your time. Bye-bye.